November 17, 1943. Dawn broke over WWII airstrip in New Guinea with the thick scent of fuel and oil hanging in the tropical air. Staff Sergeant Tony McKenna knelt beneath the belly of a P-38 Lightning, his hands wrapped around the aileron control cables that ran through the aircraft's twin booms. The metal was cold, despite the heat already building across the airfield. He could feel it, that slight give in the cable, barely 3/8 of an inch of slack that his fingers detected but his eyes could not see. Around him, other mechanics moved through the pre-dawn ritual of preparing fighters for another mission over the Solomon Sea. The sound of wrenches against aluminum, the hydraulic hiss of landing gear tests, the distant rumble of engines warming on the flight line. McKenna had felt this slack before in every P-38 he had serviced in the past 8 months. He had mentioned it to the engineering officer. The response had been clinical, dismissive. Factory tolerances allowed for slack up to ½ an inch under operational conditions. The specification was approved. The manual referenced it. Every inspection verified compliance. If the cables measured within spec, the aircraft was airworthy. But factory specifications were written 7,000 miles away in Burbank, California, by engineers who designed control systems in wind tunnels and on paper. They had never sat in a ready tent listening to pilots describe the fraction of a second delay between stick input and aircraft response. They had never watched gun camera footage of P-38s entering hard turns just a heartbeat too late, rolling inside the turning radius of a zero just as tracers stitched across the American fighter's wing. The Japanese A6M0 possessed a turning radius of roughly 400 feet at combat speeds below 300 miles per hour. Its lightweight construction and extraordinarily low wing loading gave it maneuverability that bordered on supernatural in the hands of experienced Imperial Japanese Navy pilots. When a Zero pilot committed to a hard turn, the aircraft responded with mechanical immediacy. When a Lightning pilot pulled the same maneuver, that 3/8 of an inch of cable slack translated into a delay. Not much, perhaps a quarter of a second, but a quarter second at 280 miles per hour meant the aircraft traveled more than 100 feet before the ailerons reached full deflection. In a turning dogfight, where both aircraft were circling within a radius of 500 feet, that delay was the difference between guns on target and the enemy slipping outside your firing solution.
The P-38 Lightning had entered Pacific theater operations in late 1942 as a technological marvel. Twin Allison engines producing 1,200 horsepower each, 4 50-caliber machine guns and 1 20mm cannon concentrated in the nose, all firing along the same axis without convergence problems. A range of 1,600 miles that allowed escort missions deep into Japanese-held territory. Top speed exceeding 400 miles per hour. On paper, the Lightning was superior to the Zero in nearly every measurable category except one: low-speed turning performance. American tactical doctrine compensated for this disadvantage by emphasizing boom and zoom tactics, diving from altitude to deliver high-speed passes before climbing back to safety. The strategy was sound. The execution was complicated by the reality that not every engagement began with altitude advantage, and not every diving attack resulted in a kill. Sooner or later, most P-38 pilots found themselves in turning fights with Zeros, and in those turning fights, American pilots were dying. The kill ratio told the story in numbers that couldn't be argued with. In the Mediterranean theater, where P-38s faced Messerschmitt Bf-109s, German pilots established a victory-to-loss ratio approaching 3 P-38s for every Bf-109 destroyed. In the Pacific, the numbers were less definitive but equally troubling. Early missions in late 1942 and early 1943 saw P-38 squadrons claiming favorable kill ratios. But detailed analysis of Japanese records revealed that actual enemy losses were significantly lower than American claims. On missions where P-38s engaged substantial numbers of Zeros, the Americans often lost aircraft or returned with severe battle damage. One mission in early 1943 resulted in American pilots claiming 6 Japanese aircraft destroyed at a cost of 1 P-38 shot down and 1 returned so badly damaged it was written off. Japanese records showed no Zeros lost. Pilot accounts from these engagements consistently describe the same phenomenon. The P-38 felt sluggish in hard maneuvering, like the aircraft was responding to control inputs made seconds earlier, rather than in real time.
McKenna understood the mechanical explanation. The P-38's aileron control system ran cables from the cockpit control yoke through the twin booms to the tail section, then forward through a series of pulleys to the wing control surfaces. The system was conventional, mechanically direct, and theoretically precise. But cables stretch under load. They wear with use. Temperature changes cause expansion and contraction. Every cable-controlled aircraft in service developed some degree of slack over operational hours. Lockheed's engineers had accounted for this reality by specifying tolerance ranges that allowed up to half an inch of slack. The thinking was logical. Some slack was inevitable, so build it into the specification. Too much tension would risk cable failure or binding that could lock controls. The approved range represented a compromise between zero slack, which was mechanically impossible to maintain, and excessive slack, which would degrade control response. But the specification was based on assumptions about normal flight operations. It didn't account for combat maneuvering at the edge of the aircraft's performance envelope, where pilots yanked control yokes with desperate force, and aircraft responded to maximum deflection inputs dozens of times per mission. The unauthorized modification McKenna had been contemplating for weeks required only simple materials: a 6-inch length of piano wire salvaged from a damaged aircraft, standard tools available in any forward combat zone, 8 minutes of work. He bent the piano wire into a Z-shaped configuration that would maintain constant tension on the control cables while allowing for thermal expansion and normal operational flexing. The Z-shaped provided spring-like characteristics, automatically adjusting cable tension as operational conditions changed while preventing over-tensioning that could damage cables or cause binding. The elegant simplicity of the device masked its mechanical sophistication. McKenna positioned the wire tensioner at the critical junction point in the cable system, where slack typically accumulated, installing it so the modification would hold precisely 0.4 pounds of additional tension. It eliminated the 3/8 inch of slack completely. The control cables now ran taut from yoke to aileron with zero perceptible give. When he tested the system by moving the control surfaces manually, the ailerons responded with immediate precision. No delay, no softness in the initial movement. The mechanical connection between pilot input and control surface deflection was now direct in practice as well as theory. Lieutenant James Hayes climbed into the modified P-38 on the morning of November 18th without knowing his aircraft was different from any other Lightning on WWII. The pre-flight briefing had been routine: sweep over Rabaul, engage enemy fighters if encountered, return to base. Hayes was a competent pilot with 11 missions under his belt and no confirmed kills. He belonged to the category of pilots the squadron commander worried most: skilled enough to survive the first few missions through caution and defensive flying, not yet experienced enough to press attacks with the aggressive confidence that resulted in victories. Hayes taxied to the runway at 7:42 in the morning. McKenna watched from the maintenance area, saying nothing to the inspection crew or the engineering officer. The P-38 accelerated down the coral runway and lifted into air that was already building with tropical heat. By the time the formation reached 10,000 feet and turned northwest toward New Britain, McKenna was already working on another aircraft, calculating which modification would go unnoticed by the morning inspection crew.
The combat encounter occurred at 11,000 feet over the Solomon Sea. 16 P-38s from the 475th Fighter Group intercepted a formation of Japanese aircraft returning from a raid on Allied positions. The engagement fragmented immediately into individual dogfights as Zeros turned to meet the American fighters. Hayes found himself in a climbing turn with a Zero at his 4 o'clock.
The Japanese pilot executing a hard left turn that would bring him onto Hayes's tail within seconds if the American couldn't match the turn rate. Standard doctrine called for Hayes to roll right, extend in a dive, and use his superior speed to disengage. Instead, Hayes pulled hard left, committing to a turn fight. The control yoke moved in his hands. The P-38 rolled and kept rolling. The response was immediate, precise, without the slight delay Hayes had unconsciously learned to anticipate. His brain, trained by dozens of hours in standard P-38s, had developed the habit of leading his control inputs to compensate for the lag. Now there was no lag. The aircraft responded to his reflexes, rather than requiring him to predict where it would be a quarter second in the future. The Zero pilot executed a hard climbing spiral, a classic maneuver designed to exploit the Japanese fighter's superior climb rate and turning radius. Hayes stayed with him. The two aircraft circled each other in a vertical helix that tightened with each revolution. The Zero should have been pulling inside Hayes's turn radius. It wasn't. The P-38 was matching the Japanese fighter's movements with precision that shouldn't have been possible. Hayes could feel the difference in his hands, in the way the aircraft responded to minute adjustments of the control yoke. When he rolled right to follow the Zero spiral, the Lightning snapped through the maneuver like it weighed half its actual mass. The enemy pilot recognized something was wrong. His tactical assumptions about P-38 performance, developed through combat experience against dozens of American fighters, no longer applied. He attempted to reverse his turn, rolling hard right to exploit what should have been a moment of sluggish response as the P-38's controls reversed direction. Hayes reversed with him. The Zero filled his gun sight. He fired a 2-second burst. The 450 caliber machine guns and 20mm cannon concentrated their fire into a space less than 3 feet across. The Zero's left wing separated from the fuselage. The aircraft tumbled into an uncontrolled spin and disappeared into the cloud layer below. Hayes returned to WWII at 1:15 in the afternoon, his gun camera footage showing a kill so clean that the squadron intelligence officer initially questioned whether it was genuine. P-38s didn't win turning dogfights with Zeros. The mathematics of wing loading and power-to-weight ratio made such victories nearly impossible for pilots of comparable skill. But the gun camera evidence was unambiguous. The intelligence officer wrote his report. Hayes described the engagement, mentioning almost casually that his aircraft had felt unusually responsive. The comment was noted, but not emphasized. What happened over the next 72 hours would change P-38 combat effectiveness across the Pacific faster than official engineering channels could document.
McKenna's modification had not been subtle in its effect. It had been invisible in its installation. When the maintenance crew inspected Hayes' aircraft the following morning, they found nothing out of specification. The cable tension was within tolerances, the control surfaces moved freely, the system showed no signs of unauthorized work. But Hayes' casual comment about improved responsiveness had reached other pilots. 3 of them approached McKenna directly. They didn't ask what he had done. They asked him to do it to their aircraft. By November 21, 8 P-38s at WWII had been modified. All of the modifications were installed during evening maintenance periods when inspection procedures were less rigorous. None were documented in maintenance logs. The engineering officer, still 7,000 miles away in California, had no knowledge that field mechanics were systematically altering flight control systems on combat aircraft. The combat results appeared in squadron reports within 2 weeks. Pilots flying modified aircraft reported improved control response in hard maneuvering situations. Kill ratios began shifting. Squadrons equipped with modified P-38s saw their victory-to-loss rates improve from unfavorable to nearly even within 30 days. More significantly, pilots' survival rates increased as improved control response allowed defensive maneuvers that had been impossible with standard cable slack. The difference was measurable in data that squadron commanders couldn't ignore. Pilots who had survived on defensive tactics and boom and zoom discipline began pressing attacks in turning engagements.
the psychological impact proved as important as the tactical advantage. American pilots gained confidence in their aircraft's ability to engage Japanese fighters on more equal terms. That confidence translated into more aggressive combat flying, which produced more opportunities for successful attacks, which further reinforced the pilots' willingness to engage.
The modifications spread through unofficial channels faster than any technical bulletin or engineering directive could have traveled. Mechanics talked to mechanics. Squadron maintenance officers shared techniques during supply runs to rear area bases. Within 6 weeks of McKenna's first installation, P-38 units across New Guinea and the Solomon Islands were implementing variations of the wire tensioner system. Some mechanics used piano wire. Others adapted steel cable from other damaged aircraft. Some fashioned tensioners from springs salvaged from landing gear assemblies. The diversity of materials demonstrated both the desperation for improved performance and the mechanical ingenuity of combat veterans who understood their aircraft better than distant engineers. All variations share the fundamental principle: eliminate the cable slack that degraded control response. The implementation details were less important than the operational effect. Lockheed's engineering department learned of the unauthorized modifications through official channels in late December 1943. The company's initial response was predictable. Field modifications to flight control systems violated specifications, voided warranties, and introduced unknown failure modes that had not been tested. The engineering officer who received the first report wrote a strongly worded directive prohibiting further modifications and ordering existing installations removed and replaced with standard cable tension specifications. The directive reached the Pacific Theater on January 3, 1944. Squadron commanders filed the paperwork and ignored it. Combat effectiveness had improved measurably since the modifications began appearing. Pilots were surviving engagements they would have lost 6 weeks earlier. No modified aircraft had experienced control system failures attributable to the tensioner installation. The engineering officer's concerns about voided warranties and untested modifications carried no weight with commanders who measured success by how many pilots returned from missions alive.
The confrontation between engineering authority and combat necessity reached crisis point when a modified P-38 returned to base with severe battle damage that included partial failure of the aileron control system. The post-battle inspection revealed the wire tensioner still functioning correctly, maintaining cable tension despite damage to surrounding structures. But the incident gave Lockheed's engineers the opening they needed to demand comprehensive investigation. In February 1944, a team of company engineers arrived in the Pacific Theater with authorization to test the modifications under controlled conditions. Their arrival coincided with growing recognition that the field mechanics might have solved a problem the factory had never properly acknowledged. The engineers conducted stress testing, measured control response times, and analyzed performance data for modified versus standard aircraft. The results validated every claim the pilots and mechanics had made. Control response delays were reduced by approximately 70%. Roll rates improved measurably at combat speeds. The modifications introduced no significant risk of control system failure when properly installed. The official engineering report filed in March 1944 represented an unusual admission. Factory specifications had been based on peacetime operational assumptions that didn't account for combat maneuvering requirements. The tolerance range that allowed up to half an inch of cable slack was appropriate for normal flight operations, but inadequate for the extreme control inputs pilots were executing in combat. The wire tensioner modification addressed a legitimate performance limitation that should have been corrected during the design phase. Lockheed's recommendation was to develop a standardized version of the modification and retrofit it across all P-38 variants in combat service. But the recommendation came with a caveat. The field-expedient tensioners, fabricated from salvaged materials without standardized specifications, would be replaced by factory-engineered components manufactured to precise tolerances. The engineering department, having acknowledged the combat necessity of the modification, now insisted on controlling its implementation.
The bureaucratic response was simultaneously validation and frustration. McKenna and the other mechanics who had risked court-martial charges by modifying flight control systems without authorization were vindicated in their assessment of the problem. But their elegant, simple solution, a bent piece of piano wire installed with standard tools, was deemed insufficient for official adoption. The factory-engineered replacement was a complex assembly of springs, tensioning devices, and adjustment mechanisms that accomplished the same function with 5 times the parts count and 10 times the weight. The official modification kits began reaching Pacific squadrons in May 1944. Installation required 16 hours of work compared to McKenna's 8 minutes. The performance improvement was identical to what the field-expedient modifications had achieved 6 months earlier. But the official version satisfied engineering documentation requirements, provided consistent installation standards, and could be incorporated into production aircraft being manufactured in Burbank. The bureaucratic victory was hollow. By the time official modification kits reached combat squadrons, most P-38s in the Pacific Theater had already been modified using field-expedient methods. The official kits were dutifully installed on aircraft rotating through rear area maintenance facilities for major overhauls. But front-line squadrons continued using the wire tensioners that their mechanics had fabricated. The performance was identical. The installation was faster. The parts were free, salvaged from damaged aircraft rather than requested through supply channels that took weeks to deliver components. Squadron commanders tacitly accepted the situation. The engineering officers' reports noted discrepancies between official modification status and actual aircraft configurations, but made no serious attempt to enforce compliance. Japanese intelligence services eventually identified the source of improved P-38 performance through examination of captured aircraft. Analysis of the wire tensioner modifications revealed sophisticated understanding of control system dynamics that Japanese engineers had not anticipated from American field mechanics. The discovery forced revision of Japanese tactical doctrine. The assumption that P-38 control limitations would provide exploitable advantages in turning engagements was no longer valid. Japanese pilots were instructed to avoid sustained turning dogfights with Lightnings unless they possessed overwhelming altitude or numerical advantage. The tactical shift represented acknowledgement that American technical adaptability had eliminated a key advantage Japanese fighters had enjoyed for the first year of Pacific combat operations. The Zero's superior low-speed maneuverability remained unchanged, but the gap between Zero and P-38 turning performance had narrowed enough that American pilots could now survive and occasionally win engagements that would have been suicidal 12 months earlier. The wire tensioner became a symbol of something larger than its mechanical function. It represented the gap between engineering theory and combat reality, between specifications written in California and requirements discovered over New Guinea. Every piece of piano wire bent into a Z-shape and installed in a P-38's control system was a quiet rejection of the idea that factory engineers understood combat aircraft requirements better than the mechanics and pilots who flew them into battle. The modification worked because it addressed a real problem that official channels had dismissed. It spread because mechanics trusted each other's judgment more than they trusted engineering directives written by people who had never heard a Zero's engine note or watched gun camera footage of American pilots dying because their aircraft responded a quarter second too slowly. The improvement in P-38 combat effectiveness continued through 1944 and into 1945 as other modifications and tactical refinements compounded the advantages gained from improved control response. Dive recovery flaps, introduced on the P-38J-25 variant in early 1944, solved the compressibility problems that had plagued the aircraft in high-speed dives. Hydraulically boosted ailerons on later models further improved roll rates at high speeds. Better tactics, improved pilot training, and growing experience against Japanese fighters all contributed to shifting kill ratios. By 1945, P-38 pilots in the Pacific Theater had destroyed more than 1,800 Japanese aircraft. 7 of the top 8 American aces in the Pacific flew Lightnings. Major Richard Bong achieved 40 confirmed victories before his death in a P-80 crash in August 1945. Major Thomas Maguire scored 38 kills before being killed in a low-altitude crash in January 1945. These achievements reflected not just pilot skill, but the cumulative effect of technical improvements that had transformed the P-38 from a capable but flawed aircraft into one of the most effective fighters in the Pacific. But the wire tensioner modification remained foundational to all subsequent improvements. Control response was the basis upon which every other advantage was built. Dive flaps were worthless if the pilot couldn't precisely control the aircraft during recovery. Hydraulic boost was meaningless if cable slack absorbed the input before boost systems could engage. Tactical doctrine assumed immediate control response. If that assumption was wrong, the tactics failed. McKenna's 8-minute modification, unauthorized and undocumented, had fixed the foundational problem that made everything else possible.
The official history of the P-38 Lightning, written after the war, made no mention of field-expedient control cable modifications or the mechanics who implemented them without authorization. The engineering report filed in March 1944 was classified and remained unavailable to historians for decades. Lockheed's corporate history emphasized the factory-engineered solutions to combat performance limitations, the dive flaps, the hydraulic boost systems, the improved engines, and increased fuel capacity. The story of unauthorized modifications installed by mechanics working at night to avoid inspection procedures didn't fit the narrative of American technical superiority achieved through engineering excellence and industrial capability. But every P-38 pilot who returned from a mission alive, because his aircraft rolled cleanly into a defensive break without that quarter-second delay, owed something to a staff sergeant kneeling beneath a Lightning at dawn, feeling with his fingers the slack that specifications said was acceptable, but combat experience said was fatal. The wire tensioner itself, bent from salvaged piano wire and installed with standard tools, embodied a particular kind of American pragmatism. It wasn't elegant engineering. It wasn't sophisticated technology. It was a simple mechanical device that solved a specific problem using available materials and practical knowledge. The Japanese Zero represented one philosophy of fighter design: minimized weight, maximize maneuverability, sacrifice protection and firepower for performance. The P-38 represented another philosophy: used powerful engines and advanced technology to achieve performance through brute capability rather than elegant efficiency. But the wire tensioner represented a third philosophy: trust the people closest to the problem to develop solutions, even if those solutions bypassed official channels and contradicted engineering authority. That philosophy, as much as any technical specification or tactical doctrine, defined American air power in the Pacific. It was the philosophy that also produced the field kits to upgrade the mounts on the Cal 50 caliber machine guns in B-17s, from single pintle mounts to twin pintle mounts capable of doubling firepower. And it did not fit the narrative that P-38 pilots actually thought less of drop tanks and bombs and more of kneeling mechanics, a solid adjustment, and fresh piano wire.
November 17, 1943 to May 1944.
6 months from the first unauthorized modification to official engineering approval. In that period, the balance of air combat over the Pacific shifted measurably. The Zero remained a formidable opponent, dangerous in the hands of experienced pilots, deadly in situations where its advantages could be exploited. But it was no longer invincible. American pilots were no longer resigned to flying defensively, avoiding turning engagements, surviving through caution rather than winning through aggressive combat. The change wasn't attributable to a single factor. Better tactics, improved training, numerical superiority, and cumulative attrition of experienced Japanese pilots all played roles. But the foundation was control response. The ability to make the aircraft do exactly what the pilot intended, exactly when he intended it, without delay or compromise. That foundation was built with bent piano wire and mechanical instinct, installed 8 minutes at a time by people whose names appeared in no official histories, but whose work determined who lived and who died in the sky over the Solomon Sea. The wire tensioner worked because it addressed the simplest possible problem in the simplest possible way. 3/8 of an inch of cable slack eliminated by 0.4 pounds of additional tension. No complex calculations, no advanced materials, no sophisticated manufacturing required. Just a clear understanding of cause and effect, implemented by someone who trusted his hands and his experience more than he trusted specifications written by people who had never watched a P-38 roll into a turn a heartbeat too late. In the end, that was what the modification represented: the judgment that combat effectiveness mattered more than engineering authority, that survival justified unauthorized action, and that the people closest to the problem understood it better than the distant bureaucracy charged with solving it.
The war in the Pacific would continue for 15 more months after Lockheed officially approved the control cable modification. Thousands of P-38 sorties would be flown. Hundreds of Japanese aircraft would be destroyed. Dozens of American pilots would die. The Lightning's contribution to Allied victory would be measured in statistics about kill ratios and ace pilots and missions flown. But beneath all those numbers was a simpler truth. American pilots could fight the Zero on more equal terms because a staff sergeant in New Guinea had trusted his judgment over his orders, had felt with his fingers a problem that specifications said didn't exist, and had fixed it with salvaged wire and 8 minutes of work. That truth, more than any statistic or official history, captured what made American air power effective. Not superior technology or engineering excellence or industrial capacity, though all those mattered, but the willingness to trust practical knowledge over theoretical authority, to solve problems with available resources rather than waiting for perfect solutions, and to accept that the people doing the work often understood it better than the people writing the rules. The bent piece of piano wire, Z-shaped and tensioned to 0.4 pounds, wasn't recorded in official histories. It wasn't mentioned in engineering reports or commemorated in museums. But it was there, in every P-38 that rolled cleanly into a defensive break, in every pilot who returned from a mission that should have killed him, in every combat report that noted improved control response and better survival rates. The wire tensioner was a ghost in the machine, invisible but essential, unauthorized but vital. It represented the gap between what was specified and what was necessary, between what was approved and what worked. And in the Pacific Theater between November 1943 and the end of the war, that gap was measured in cable tension, control response, and lives, saved by mechanics who knew better than to trust specifications written 7,000 miles from combat.